Hello everyone, welcome to Joining Hub. This is Sanjana, and in this video we will be continuing with part 5 of distributed computing of module 1. In the previous sessions we have already discussed about the basics of distributed computing, features of distributed system, what middleware is, motivation, the primitives for distributed communication, what blocking, non-blocking, synchronous, asynchronous primitives are, the 4 versions of send primitives: synchronous blocking, synchronous non-blocking, asynchronous non-blocking, and all those things. And then we have also studied about comparisons of those and processor synchrony, and also libraries and standards. In this video, we will be continuing with design issues and challenges. If you want to get more clarifications on the previous topics, please visit and watch those videos which is already there in the channel. Design issues and challenges. When we build a distributed system, we cannot simply connect a few computers and expect everything to work perfectly, right? Unlike a single computer, a distributed system consists of many independent computers connected through a network. Therefore, while designing such a system, engineers must solve several problems. These problems are called design issues and challenges. The classification of design issues can be categorized into 3, as you can see over here: system design, algorithm design, and applications. System design and operating system related. Here it involves designing the overall architecture of the distributed system. Example like communication, naming, synchronization, security, fault tolerance. These things decide how the distributed system should work. Then algorithm design related. These involve designing efficient algorithms that allow distributed computers to coordinate with one another, how they can coordinate, like load balancing, distributed graph algorithm, global state, replication, consistency, and all those things. The third one is emerging technology related, the applications. These arise because of modern technologies like mobile computing, grid computing, sensor network, peer-to-peer network, and these are newer application areas of distributed computing. First one is distributed system challenges from a system perspective. In this, we will be studying about 10 functions: communication, processes, naming, synchronization, data storage and access, consistency and replication, fault tolerance, security, applications programming interface, API and transparency, scalability and modularity. First of all, what is communication? Okay, design issues. What is design issues? These are the issues every engineer must consider while designing a distributed system. When they want to design a distributed system, what all things they should know, what all issues that can occur that they have to know. That is design issues. The first one is communication. Communication, by the way, communication is the heart of distributed system. We have already learned in the previous session that distributed system have no shared memory. Hope you remember that. And communication is done by exchanging messages. Every process depends on communication to coordinate with another. Only then they can coordinate, because there is no shared memory. Hope you remember that. Then the question comes, which communication protocol should be used? Should communication be asynchronous or synchronous? Should communication be blocking or non-blocking? How can messages be delivered reliably? What happens if a message is lost? And all these belong to the communication design issue. Let us take an example. When you send a WhatsApp message, your phone communicates with WhatsApp server and it goes to your friend's phone. Reliable communication here ensures that message eventually reaches the receiver. That is communication. Then we have processes. Processes are distributed system contain many processes executing simultaneously. And these processes may have to cooperate, sometimes compete, and then communicate with each other. And the designer must decide how should processes be created, how should they communicate, how should they terminate, how should they share work. These things have to be decided. Example, Google search. There is one processor receives search request, and another will go search database, another will rank the results, and another one will display the web page. That is processes. Then we have naming. Naming, suppose there are 1,000 computers. How do you identify one specific computer? That is using names. Every resource must have a unique identity like IP address, URL, domain name, process ID. It is really hard to remember 142.250.183.46, that is IP address. It is really hard to remember. Instead, what we can do, we can type www.google.com. The naming service that will convert the name into correct address. Why it is important? Because without naming, computers would never know where to send the message. That is why naming is important. Then we have synchronization. Synchronization means coordinating multiple processes. Remember, we do not have a common clock and distributed system. Therefore, processes must synchronize their action. Example, suppose two users try to book the last railway ticket. So they are trying to do it at the same time. Without synchronization, what will happen? Both may get the ticket. Synchronization helps prevent such conflicts. In later modules, we'll be learning about logical clocks, leader election, mutual exclusion, and all. These are all used to solve synchronization problems. Then we have data storage and access. Data is distributed across many computers. Then the question comes, where should data be stored? How should users access it? Should data be replicated? Here example, we can take Google Drive. Files are stored across multiple data centers. Users don't know where the file is physically stored. Right? That is data storage and access. Then we have consistency and replication. These two terms actually always appear together. Why? Replication means keeping multiple copies of the same data. Suppose your Gmail inbox is stored in India and Singapore. If one server crashes, there is still another copy, right? What is the advantage of this replication? Higher reliability, better availability. What about consistency? Now imagine there are 100 emails and you delete one email. So should both copies update? Yes, both the copies. You have one copy in India and one copy in Singapore. If only one copy is being deleted, one server will show 100 mail and another one will show 99 emails. This can create inconsistency. So consistency means all copies of the replicated data should remain identical. That is consistency. Then we have fault tolerance. Fault tolerance is something, failures, we cannot predict failures. They are unavoidable. Computers can crash, networks can fail, power may go out. So, and despite all these situations, the system should continue working. For example, in Netflix, there are 1,000 servers. If one server crashes, it should not affect the streaming. The streaming should continue. That is about fault tolerance. And in fault tolerance, different methods like replication, backup, checkpointing, recovery, all those things are some methods for fault tolerance. We'll be studying that in detail in module 4. Then we have security. Distributed system communicate through network, and therefore security is very essential. Security usually includes authentication, authorization, encryption, data integrity, confidentiality, and all those things. For example, online banking. If there is no encryption, hackers could easily steal the passwords because there is no encryption, there is no safety in that, there is no security in that. Then we have application programming interface and transparency. API means application programming interface. This API provides a standard way for applications to use distributed services. Example, programmer simply writes send message function. Why? Because instead of implementing the entire communication protocol, that they can just call that particular function. We have already learned this in detail in the previous sessions. Then coming to transparency part, it is one of the most important concepts. Transparency means hiding the complexity from the user. User only sees one computer, but in reality there are thousands of servers. And these are different types: access transparency, location transparency, replication transparency, and all. Access transparency, okay, remember the basic concept of transparency is hiding the complexity. So what does access transparency mean? Same way to access local and remote resources. Whereas location transparency is where user will not know where the resource is. Migration transparency is where resource can move without affecting users. Replication transparency, multiple copies appear as one in replication transparency. In failure transparency, system continues even if some component fails. Then we have concurrency transparency, multiple users access simultaneously without conflict. Then there is one transparency, the persistence transparency. Here data survives even after the program stops. That is persistence transparency. Then we have scalability and modularity. Scalability means the ability to handle more users simply by adding more machines. For example, in Instagram, there are 1,000 users and on the next day it becomes 10 million users. Then you'll have to add more servers. That is scalability. The size. Modularity. Modularity, instead of using one huge application, we can divide that into modules. Why are we learning one subject in 5 different modules? Because that is easier for the students to study. Similarly, in Amazon, we have a payment module, we have orders module, recommendation, delivery. Each of these run independently, but together as a huge one application, we have that as a website. That is about scalability and modularity. Next, we are moving to algorithmic challenges in distributed computing. Algorithmic challenges, first one, we have execution model, distributed graph algorithms and all. First one is execution models. Designing models that describe how distributed programs execute. It can be synchronous model, asynchronous model. So it is a designing model. We should know how the distributed programs execute. Then we have distributed graph algorithms and distributed routing algorithms. Many distributed systems are represented as graphs, and these algorithms solve routing, broadcasting, shortest path, leader election. All these things can be solved using these graph algorithms. Then we have time and global stage, which is very important because we should know there is no global clock determining which event happened first. It will be very difficult to determine that. That is why we use logical clocks to solve it. That is time and global state. Then synchronization mechanism. How can computers coordinate without a common clock? Those can be solved using algorithms such as Lambert clock, vector clock, mutex, leader election, and all those things. These can be solved in those ways. I have written these in detail. Then you have group communication. Instead of sending one message to one computer, sometimes one message must reach many computers. That is called multicast. And the ordering is also important. Everyone should receive message in the correct sequence. Okay, we are looking at the algorithmic related thing. Okay. That is group communication, multicast, and ordered message delivery. Then monitoring distributed events. Suppose you want to know whether every server has completed its task. Monitoring becomes difficult. Monitoring becomes difficult, and algorithms observe distributed events and detect system-wide conditions. Then we have debugging distributed programs. It is really harder than debugging ordinary program. Why? Because many computers execute simultaneously in this, and errors may depend on message timing. Then we have data replication, consistency models, and caching. Caching is to improve speed. Replication improves reliability. Consistency ensures all copies remain identical. Then we have World Wide Web design, WWW, caching, searching, scheduling. In this World Wide Web design, challenges include caching, searching, scheduling. Google search is one of the good example of WWW design. Then we have distributed shared memory abstraction. Even though there is no shared memory, the system tries to create an illusion of shared memory. We'll study that in module 4. Then we have in the distributed shared memory abstraction itself, there are different things you should know, like weight-free algorithm, mutual exclusion, register construction, consistency model, consensus algorithm, replication and replica management, voting and quorum system, distributed databases and distributed commit, self-stabilizing system, checkpointing and recovery algorithm, failure detectors. These will be learning in module 4. Okay. Then we have load balancing. Load balancing is where suppose you have a server A and that server A has 1000 requests and there is server B which has 100 requests. Load balancing moves work to avoid overload. Example, Amazon during big billion days, traffic is distributed across many servers. Will help to balance the server, that is load balancing. Then real-time scheduling. Real-time scheduling, some applications have deadlines. Example, air traffic control, hospital monitoring, late responses. Can be dangerous in these situations. So real-time scheduling is important. Then performance. Performance means fast execution, low delay, high throughput, efficient resource utilization. Those are performance, that those come under performance. Then we have applications of distributed computing and newer challenges. First one, these are actually modern application areas. First one is mobile computing. Mobile systems. Mobile system where is usually of wireless communication, which is based on electromagnetic waves and uses a broadcast medium. You can take the example of smartphone. It communicates with cloud server. Then we have base station approach and ad hoc network approach are the two popular architecture for a mobile network. Then we have sensor network. Sensor network, there are thousands of sensors. It will collect temperature, humidity, traffic and all those things, and we can get whatever thing, we can sense the physical parameters. It can be mobile or static. It can communicate wirelessly. The sensors also can communicate wirelessly. Then we have ubiquitous or pervasive computing. So here computing available everywhere. Example is smart home, that is pervasive computing. Then you have peer-to-peer computing. In peer-to-peer computing, every computer acts as a client and server. Example like BitTorrent, that is peer-to-peer computing. Then publish subscribe system or publish subscribe content distribution and multimedia. Very good example of that is YouTube notification. That is, publisher will send data and subscribers will receive the updates automatically. YouTube itself is one of the very good example of publisher subscribe systems. Then we have distributed agents. Distributed agents, here independent software agents will cooperate to solve problems. That is distributed agents. Then distributed data mining. Here large data sets are processed across multiple computers. That is distributed data mining. Then we have grid computing. Grid computing is where many geographically distributed computers will combine their computing power. Example, scientific research, weather prediction, protein folding and all. That is grid computing. Then we have security in distributed system. Remember, modern distributed system must protect data, users and communication against cyber attacks. Therefore, security is very important. Confidentiality. So, three challenges of security are, first one, confidentiality. Confidentiality means only those people who have authorization can access information. That is confidentiality. Authentication is where we are making sure if the information we have received from the source is genuine or not. Availability is allowing access to services despite the malicious action. That is security in distributed system. So we have learned the design issues in that communication processes, naming, synchronization, data storage, consistency and replication, fault tolerance, security, API, transparency, scalability, modularity, all those things came. In algorithmic challenges, we had execution models, time and global state, group communication, debugging, load balancing, performance, then distributed shared memory and all. Then applications, we studied about mobile systems, sensor network, grid computing, peer-to-peer computing, distributed data mining, then publish, subscribe, distributed agent security, and all those things. In the next video, we'll be discussing about models of distributed computation. So till then, bye bye.